All right, so what we're trying to do is we're trying to take the square root of each of these numbers and leave them in simplest radical form. This is not something you want to do with a calculator, just like to punch the button in and get a decimal. We want to leave it in simplest radical form. So the way I always do it, if I'm not seeing it immediately, I'm just going to take it and I'm going to break it down. I like to find the smallest prime numbers that I possibly can. So here I've got 168. That last number is even. I know for a fact a 2 goes in. What's half of 168? 84, right? And then I'm going to keep breaking that down. Now, am I saying that this is the way that you have to do it? No. But by writing it down like this, you organize yourself. So we got a 2, a 2, a 2, a 3, and a 7. Those are all of our primes. And I'm going to say, all right, well, I want to find perfect square pairs. So here's a pair of 2s. Remember, 4 is a perfect square. When we square root that, we get a 2. The rest of these, notice they can't make a pair. I don't have any other 2s. I don't have any other 3s. I don't have any other 7s. So these are going to stay on the inside, and then this is what's going to be on the outside. So we got a 2 coming out, and then on the inside, 2 times 3 times 7. Well, 7 times 3 is 21, times 2 is 42. So 42 stays in here because this 42, you can't break it down anymore. And that's okay. It's okay that you can't break it down anymore, but it's important to recognize that, right? All right, let's take care of this next one. 504. So I'm going to go through. I'm going to do the same exact thing. Again, I like to start with 2s when I can because those are the easiest to work with. I see that the last number is even. That means I'm dividing this half of 504. 252, right? Well, look, I can still divide by 2 again, right? I think 2 goes into 2 once. 2 goes into 5 twice. 2 goes into 12 6 times. Yeah. All right, then we can keep going, right? There's still a whole factor 2 I can go with, right? 126, 6 is even. Half of 12 is 6, half of 6 is 3. 63, well, I can pull a 3 out of that one, right? That's 21, 3, and 7, right? So I'm going to go through. I'm going to say, all right, let's line them up. 2, 2, 2, 3, 3, 7. Once again, let's identify our perfect square pairs. 2 squared is 4. Square root of that is 2. This other 2 doesn't get a pair. I've got a pair of 3s. 3 squared is 9. 3 times 3 is 9, right? The square root of that is 3. And then 7 doesn't have a pair. So what goes on the outside? 2 times 3. What goes on the inside? These leftovers. 2 and 7, which is 14. And that's that right there. Let's continue on. I want 512. Again, I'm breaking it down. Well, what goes into 512? Again, start with the lowest numbers that you can. Start with like 2. Try and break down 2, right? Well, you break down 2. Well, what's half of 512? Let's do it again. What's half of 256? What's half of 128? What's half of 64? What's half of 32? What's half of 16? Right? We keep on going. Then we break this one down. So let's count all the twos. 1, 2, 3, 4, 5, 6, 7, 8, 9 twos, right? And then again, make pairs. And then there's one left over. So what do we have? We've got to these the perfect square of 4, 2, 2, 2, and 2. These is what's coming out. 2, 2, 2, 2. 16, right? 2 times 2 is 4, times 2 is 8, times 2 is 16, and then what's left over is a 2 on the inside, because this one didn't have a pair. All right, last one, 324. Well, let's break that one down. Once again, start with the smallest number you can, 2, right? What's half of 324? Okay, let's do 162. What's half of that? What's half? Well, we can't do half of 81 anymore. Let's go up to 3, right? 3 goes into 81 for sure, right? 3 and 27. And then 3 goes into 27. And then 3 goes into 9. So let's look 2, 2, 3, 3, 3, 3. Here's a pair of 2s. Here's a pair of 3s. Here's a pair of 3s. Square root of each of these. 2 times 3 times 3, that's 18. And then what do we put in the square root? Well, what's left over? Nothing. So there's nothing that goes in a square root. 324 is actually 18 squared. 18 times itself is 324, right? We can double check that to make sure. Yeah. So there's no radical left over for this one. We used up all the numbers, so there's nothing that we have to put in storage, right? So that is going to be one of the basic skills we're going to need to be considerate of as we're doing today's topic, which is about using the Pythagorean theorem and its converse. So I'm sure for forever y'all have been talking about the Pythagorean theorem. We've even used it before in this class. The leg squared plus the other leg squared equals the hypotenuse squared. The sum of the squares of the legs equals the square of the hypotenuse. And that's all well and good, but what we're going to start doing is we're going to start branching out a little bit. We're no longer going to be saying, all right, well, we've got a right triangle. Let's figure out what the missing side is. We'll start out with that, yeah. But where we want to get to is, all right, well, is this a right triangle? Could it be obtuse? Could it be acute? How do I know? How can I figure that out? So that's what we're going to do. The Pythagorean theorem works both ways. If you've got a right triangle, then leg squared plus leg squared equals hypotenuse squared. But it flips around. If leg squared plus leg squared equals hypotenuse squared, then we know that the triangle is a right triangle. But likewise, since this is one of those back and forth type of things, if it's not true, if leg squared plus leg squared does not equal hypotenuse squared, then we can actually say, well, okay, maybe it's acute, maybe it's obtuse. And then how do we figure out the difference? All right. So, we've talked about the Pythagorean theorem before. And so, this is real common. A squared plus B squared equals C squared. When I was talking earlier, I was using this. What you need to know is that A and B are sort of dealer's choice. You, as the person doing the problem, can sort of say, well, I want this one to be A, I want this one to be B. As long as you identify whatever this value is as the hypotenuse, because see how it's opposite the right angle. As long as this one is the same for everybody, then these two can be any of the other two. You get to pick. Now, in a situation where we've got all three and we're trying to just sort of allocate and all that, I like to go, me personally, I like to go small, medium, large. That's just me because I want to keep myself consistent. I want to keep myself honest. I want to make sure that I'm always doing it right. So I'm always going to do that. But like in the end, it's kind of your choice. In the end, it's kind of what your decision is, as long as the hypotenuse is the side opposite the right angle, as long as that's what you put here. Otherwise, you're fine. All right. Now, this, I don't know if this is something that you've talked about previously in, whenever you first learned the Pythagorean theorem in middle school. But we talk about Pythagorean triples. A Pythagorean triple is just a set of three numbers that when you plug them into the Pythagorean theorem, they make the Pythagorean theorem work. To say it another way, if your sides line up to be a Pythagorean triple, like if you've got like this one, if you've got 3, 4, 5 like that, then if you plug those numbers into the Pythagorean theorem, you get a true statement, which means that these are right triangles. So if you go through and you plug them in and they work for the Pythagorean theorem, you know two things. Number one, the triangle that has the sides that you've been told is a right triangle, and the three numbers that you have used just now represent a Pythagorean triple. Now, I want to point something out here, is that by similarity, remember, as long as the sides are proportional, you've got a similar triangle, right? That means that all the angles are the same. So if if 3, 4, 5 works, well, if I multiply everything by 2, 6, 8, 10, that still is going to be a right triangle. 9, 12, 15, 12, 16, 20, 30, 40, 50, 300, 400, 500, right? Any multiples of a known Pythagorean triple is also a Pythagorean triple. That's just a fact based on what we talked about last unit with similarity. If you double the length of the sides consistently, the angle measures stay the same. Therefore, you still have a right triangle. All right. Now, I'm not going to require you to memorize any of these or anything, but what I will tell you is that if you have some of these in your brain as you're going through, oh, this is a Pythagorean triple. Most common one is 3, 4, 5. And I'll tell you, if you see either, a 3, 4, 5 triangle or some multiple of 3, 4, and 5, 6, 8, 10, 30, 40, 50. If you recognize that, that's a shortcut for you. I'm not saying that you have to memorize these things, but I am telling you, if you recognize them, that's going to save you a huge load of work sometimes. And I'm going to be very honest with you. This week, if you internalize some of these things from this week and you just have them in your brain or you have them on hand, it could make the difference between the next weeks after that being like super easy sometimes. Like, oh, wait, I don't have to do the hard way because I found this Pythagorean triple, or I found this special right triangle, or what have you. It could make the difference. It really could. But, I'm going to be teaching you sort of more and more and more complicated ways for less and less and less information. Today, you're given sort of the very most basic of situations. All right. So let's push forward. Pythagorean theorem. What's the length of the hypotenuse? Well, remember, leg squared plus other leg squared equals hypotenuse squared. Well, let's plug those in. 20 and 21, right? 20 squared plus 21 squared equals the thing we want to find squared. So one thing I want to point out, and this knowing this will make or break you. If you're the type of person that always puts X here, you're going to get screwed. X represents the missing piece. So if it's a leg, it's got to go over with the legs. If it's the hypotenuse, it's got to go with the hypotenuse. So don't just put X in the same place every time, because I guarantee you you're going to be wrong half the time. In fact, probably like 2/3 of the time, right? Because there's 3 possibilities. But if you're the type of person you don't put X in the right spot, like here, hypotenuse, this has to be this guy over here. That has to be C. Okay? So we do this. 20 times 20 is 400. 21 times 21. I think it's like 441. But I'm going to do this real quick. Yeah. Yeah. I'm going to add. And I'm looking at this and I'm saying, okay, well, what goes into 841? Because I need to leave this as like this, right? Huh. 2 doesn't go in. 3 doesn't go in, and I know this because if you take the digital root, if you add the numbers together, and the digits, what they add up to is a multiple of 3, then we know that it goes in. So this didn't go in. 2 didn't go in. 3 didn't go in. 4 won't. The last number is not a 5 or a 0, so 5 doesn't. 6 doesn't because 2 and 3 don't. Does 7 go in? 7 might go in. I don't think it's going to go in. Yeah, it doesn't go in. That doesn't come out evenly. That doesn't give us a... Well, that didn't go in. 8, 9, 10, 11. 11 might go in. So I'm specifically not using a calculator here because you won't always have a calculator. No, that's not true. That doesn't go in. I'll give it one more shot with 13, and then I'll give up. Oh, I want that. Okay. All right, let's see. 13, 26, 39, 52, 65, 78. Yeah, 78. That's 6. Goes in 61. No, that's not going to go either. Well, let's see. So basically, yeah, basically you want to just sort of buzz through the prime numbers and see what you can find. 841. Let me show you what I'm actually doing so y'all can see. There, I've got my good old scientific calculator. This is a graphing calculator, but you go through, try all the different prime numbers. Ah, this is what happens. 841. We said 4 is not going to go in. 5 is not going to go in. 6, 7 didn't go in, I don't think. Double check my work. Yeah. 9, 8 won't. 10 won't. 841 divided by 11. 841 divided by 13. 14, 15, 16, 17 might. 841 divided by 17. See how the number is getting smaller and smaller and smaller? Once the number I'm dividing by gets bigger than the number that results, I know that I'm done. All right, let's see. What other things are not 18? We already tried 3, so that's out. 19, let's try 19. 841 divided by 19. Still not. 20 won't. 21 won't. 22 won't. Let's try 23. That's the next prime number. See, we're getting close, right? 24, 25, 26, 27, 28, 29 is the next one that's prime. Hey! Oh, and that's perfect. 841 is 29 times 29. Well, doesn't that mean that this is a perfect square? What's the square root of 841 then? 29. So x is 29. Now, is this ridiculousness always going to be something that happens? No. Here, we had to like search for a number, right? And that's okay sometimes. But now we found the length of the hypotenuse. That part's done. Do the side lengths of triangle ABC form a Pythagorean triple. They're all whole numbers, no decimals, so we know that yes, this is a Pythagorean triple. All right? Your turn. Give it a try. Okay, so let's go over this. Now, I put a little triangle here. The original problem didn't give you one, but it helps to draw a picture. The legs are 10 and 24. The hypotenuse is what we're trying to find. So once again, Hypotenuse is the one on the right, yeah? So make sure that that's where the hypotenuse goes. If it was one of the legs, like we're going to do in a little bit, you'd have to put it over here. So 10 squared is 100. 24 squared is 5 something. $576. All right, so we add them up, we get 676. All right, so I know a 2 goes in here, which is great. 3, half of 76 is 38. Yeah. 2 still goes in, that's great. Half of 338. My brain's getting tired trying to do this in my head. 2 goes into 3 once. 2 goes into 13 6 times. And have 169. No 2. 3 does not go in. 4 doesn't, 5 doesn't, 6 doesn't. 7 does not. 8, 9. Let me try 13. So 13 goes into 16 once. 13 goes into 39 exactly 3 times. So 169 is in fact a perfect square, 13 times 13. So we write these out, 2, 2, 13, 13. Circle our pairs. 2 squared is 4. 13 squared is 169. So our missing side, x equals 2 times 13, 26. And then where's the square root? Well, we didn't have any leftover things, did we? No. So we're stuck here. 26. No radical left over. And are they Pythagorean triple? 10, 24, 26. They're all whole numbers. So that's a yes. All right. So now notice the hypotenuse is over here. So label, make sure that's C, and then these are A and B. Notice the X is in a new place now because it's one of the legs. Be careful there. All right. Subtract the 64 over 336. Yeah, okay. So let's break this down. It goes into 2 goes in once, 6 times, 8 times. There we go. 168 still goes into 2. Still has 2 going into it. Right. So 2, 2, 2, 2, 3, 7. These don't have any pairs with them, right? So we got a 4 on the outside from these two. Yeah. And then on the inside, we're stuck with storing this 21 as extra. And that is the length of my side, 4 times radical 21, which is a little bit more than 16 total, right? 4 times a little bit more than 4. Same idea. It's your turn now. All right, once again, we're going to go through and do this. The hypotenuse has a length of 12. I'm putting the hypotenuse down here. One leg has a length of 6, and then the other one we don't know. So let's do this. 6 squared plus the other leg that we don't know squared equals 12 squared. So let's do this. 6 squared is 36. 12 squared is 144. Subtract. That's 108. Cool. So now we're going to square root. Always check your 2's first. Half of 54. 27. So no more 2's go in, but 3 does go in. So we got 2, 2, 3, 3, 3. Once again, we're going to circle our perfect square pairs. Going to circle our perfect square pairs. And then we're going to underline the one that's left over. So what goes on the outside? 2 times 3 goes on the outside. And what stays on the inside? This leftover 3 stays on the inside. So we're left with our final answer of 6 times radical 3. And there we go. So the converse of the Pythagorean theorem. What is the converse telling us? It's saying basically, hey, if you got those Pythagorean triples, then you know you've got a right triangle. So basically, it's just going the opposite way. And how are we going to use this? Well, first of all, we're going to be able to actually answer the question, is this a right triangle? We're not going to be given any type of angles to be able to physically see. So what we need to do is we need to actually go through and say, all right, well, here are the side lengths. Does everything line up? So remember, when I do this, I make the smallest one A, the middle one B, and the biggest one C. All right? So I'm going to say, all right, well, does 13 squared plus 84, does that equal 85 squared? Are they the same? Let's find out. What's 13 squared? Well, we talked about earlier how 13 times 13 was 169, right? 84 squared, oof, that's a big number. Let's do 84 times 84. 4 times 4 is 16. 8 times 4 is 32 plus 1 is 33. 8 times 4 is 32. 8 times 8 is 64, plus 3 is 67. Add that up. 70, 56. So that's what, now we're going to add these two together. Going to get 7225, 7,225. So already that's looking good because that ends in a 5, which means that when we square it, it'll end in a 5 too. So this is, I'm optimistic that the answer is yes, but let's find out together. Let's do 85 times 85. 8 times 5 is 40, plus 2. 8 times 5 is 40. 8 times 8 is 64, plus 4 is 68. It's looking good. Add. 8 plus 4 is 12. Are these the same number? 7225, 7225. They are the same, which means that yes, this is a right triangle. Okay? So what you're going to do is you're going to take A and B, you're going to square them and add them together, and then you're going to square C, and then you're just going to compare those two. You're going to ask yourself, hey, are they the same? If they're the same, then the answer to this question is yes. Give this a try yourself. Okay, so let's go over this. Is this a right triangle? Well, once again, we're going to do the exact same thing. We're going to say, hey, what's 16 squared? What's 48 squared? What do they add up to? And is that the same as 50 squared? So what's 16 squared? 16 squared is 32, 64, 128, 256, right? 16 is 4 twos times 2 times 2 times 2 times 2. And see what I'm talking about? If you multiply by 16, 256. 48 squared. 8 times 8 is 64. 8 times 4 is 32. Plus 6 is 38. 48 times 4. 4 times 8 is 32. 4 times 4 is 16, 17, 18, 19. 4, 0, 2204. So we're going to add these. Get 2460. Now we're going to look at this one, 50 squared. Well, remember when you've got zeros on the end, you can ignore them and then put them back later. So this is really like 5 times 5 with 2 zeros on the end. Are they the same? This is not a right triangle. And we know that because we squared the legs, added them together, and they did not get to be the same as the square of the hypotenuse. Simple as that. All right, continuing forward. So if they're not the same, what do we do? So I like to base it on what C is. I like to base it on what the hypotenuse is. Hypotenuse is too big. See how C squared is bigger? Hypotenuse is smaller. So like, let's go back. I'll come back to this in a second, but let's go back. Let's look at this last problem that we just did just now. Here, the hypotenuse is 2,500. The sum of the two legs is 2,460. The hypotenuse is too big for its legs, which means that it's obtuse. So we're going to look at what the two legs add up to. Is the hypotenuse too big? Then it's obtuse. Is the hypotenuse too small? Then it's acute. All right. So we're going to do the exact same thing as we just did, but now when we compare, the answer isn't going to be yes or no, right? If the answer is that it's a right triangle, then the hypotenuse is going to be just the right size. If the hypotenuse is too big, then it's obtuse. If the hypotenuse is too small, then it's acute. Yeah? It's like the three bears. Everybody, Goldilocks and the three bears. One's too big, one's too small, one's just right. Obtuse is too big, acute is too small, and right is just right. So let's do this. The side lengths are 6, 11, and 14. Remember the two smaller ones compared to the biggest one. 6 squared is 36. 11 squared is 121. 14 squared is 196, right? Let's add these up. So we've got 157 versus 196. And so the question becomes, is the hypotenuse too big, too small, or just right? 196 is more than 157. This is too big. So this is obtuse. And that's all. Your turn. Give this one a try. So we want to go with the side lengths of 7, 8, and 9. Alrighty. So once again, we're going to go with the same exact thing we did before. We're going to take the legs, the two smaller numbers, and we're going to square those and add them together and compare them to the hypotenuse squared. Well, 7 squared is 49. 8 squared is 64. 9 squared is 81. Let's add these together. Is 113, these two legs, how does that compare to 81? Is 81 too big, too small, or just right? It's too small, right? So, since this is too small, we've got an acute triangle.